Hi, my name's Nic Brummell. I'm one of the senior participants in this KSPA, the Campus Summer Program this year. And I just want to tell you a little bit about some research work I've done in the past, and I'm still doing. This is on the emergence of magnetic structures from the deep solar interior, and it's been done with a bevy of graduate students over the years, the most recent of whom is Bishek Manek, who's a current graduate student, past graduate students. Some of you may know Jeff Vassell, Kelly Klein. Probably you guys may not have met Kelly, but oops, let's get this moving forwards. Yeah, flux emergence, solar active regions, sunspots. Most of you have seen these and seen many pictures of this type of stuff. And they're generally, when we see sort of pictures like this one over here on the left, these have led us to the belief that these active region emergence is a manifestation of tube-like structures poking through the surface. That gives us sunspot pairs. That makes sense in terms of polarities. And then it also helps us to explain all kinds of other laws and stuff which come along. I'm sure some of you have seen these diagrams before. The butterfly diagram just measures, where these active regions emerge over with time, what latitude they emerge at with time, and you get this amazing pattern. And there's polarity switching of these things, and there's tilting of these things. So there's all kinds of great constraints here on the understanding of the dynamics from observing this flux emergence of the surface. And like I said, polarities and tilts and stuff like that have become sort of more easily understood in this context of flux tubes, this idea of a flux tube poking through the surface in those pictures. More recently, there's been new observations to do with helicity. Helicity is something which measures, the different types of twistedness and connectedness of things, right? So the twist, and then the ride, and then the linkage of things. And so we can measure various types of helicities. The actual magnetic helicity is a little bit of a complicated one because it requires the understanding of a potential which generates the magnetic field itself. But there's also this thing called the current helicity, which is the curl of the magnetic field dotted into the magnetic field itself. That gives you how twisted something is around the axis in the direction it's pointing, right? So that we can measure because we can measure the magnetic field. Now, the intriguing thing about the sun is, from these measurements, is if you measure the helicity of active regions as they appear to also follow some rule. And these are called the solar hemispherical helicity rules. And what that means is that the helicity is measured in this way, of which there are many details, but we're glossing over those. The helicity is predominantly negative in the northern hemisphere and predominantly positive in the southern hemisphere. And as you can see from this plot, which shows these things where the dark circles are positive and the light circles are negative. In the northern hemisphere, there's more light circles, but there is some dark circles. So it's not a very it's not an exact rule. There's certainly scatter about this rule. In fact, it's obeyed sort of like 60%, 70% of the time. And maybe it has some cycle dependence. Oh, who knows? We don't have an awful lot of data on this, but it certainly seems to be a sort of robust, new, intriguing aspect of things measured in terms of flux emergence of active regions. So the question is, where does this come from, and can we explain this? Now, this whole tube idea, the emergence of tubes is thought to be driven in general by magnetic buoyancy. Magnetic buoyancy just says if I concentrate magnetic field in a localized region, that, seeing as the magnetic pressure, which is related to the magnetic field strength, or the magnetic energy, B squared, contributes to the total pressure. And so if I have magnetic pressure contributing, then the gas pressure decreases. And then the gas pressure is related to the density, and the density decreases. So where I have concentrations of magnetic field under certain assumptions of fast equilibration of pressure and temperature, then I have buoyant structures. Magnetic flux concentrations are buoyant, so because the density is evacuated in those regions, so they tend to rise. So this is a process this is a very hand-wavy argument of it, and you can make it much more rigorous, but that's the basic idea of why flux concentrations or structures might rise. Where do they come from? Well, there's all kinds of discussion about this stuff, and we can talk lots about that, but I'm going to assume they come from the deep interior right now. There's this region of the sun called the tachocline. I'm sure you all heard about it, which has a lot of shear, and shear is something you may need to create these strong structures. So we're assuming it comes from the deep interior. It might be from the convection zone. It may even be from the near surface shear layer, but right now I'm assuming they come from the deep interior and the tachocline. So people have played with these models of these things a lot, right? So there's the idea of a thin flux tube approximation, which just says this thing doesn't even have any cross-sectional area, it just has some buoyancy and it has something holding it back, which we'll call drag. And we can get all kinds of interesting things out of those models. We can get we can explain, or we can come with some ideas of why things emerge at certain latitudes, or what the field strengths have to be for things to emerge at the latitudes that they do, for example. These things may be completely wrong because the dynamics of that may be completely wrong. But you know, it's a simple model and it gives some ideas, and people have looked at that for years. Then you can say, well, zero cross-section is clearly not right. Let's look at fatter flux tubes. And immediately looking at fatter flux tubes with cross-sectional area, you get very different dynamics. So for example, you get a wake behind a fat thing. You don't get a wake behind a thin flux tube. You get a wake behind a fat flux tube, and wake dynamics on these things are very important. And what you quickly find is if that flux tube isn't twisted in some way, then it's very hard for it to rise. It gets ripped apart without some tension force pointing towards the center of the tube, which comes from the twist, from an axial field component, from an azimuthal field component that creates a tension, and that holds it together. And so people played a lot with these models as well. But the thing about these models is they're all saying there's an isolated flux concentration in a zero magnetic field background. And that's not really the real situation. To get away from that, you can do a couple of things. I mean, what a lot of people did says, if you want to examine the real magnetic buoyancy instability, the easiest way to look at it is to look at layers of horizontal field. So if I have horizontal field, which has a gradient in height, then there's a condition on, you know, how fast what the gradient in height is compared to what the gradient of the stratification is, which says whether instability is likely to happen. This is a much more rigorous argument rather than just saying, you know, invent a flux tube and stick it into your calculation or stick it into your theory and see what happens. This is an actual instability. You can start with a stable equilibrium, you can perturb it and look for instabilities. And if you do that, you find that, well, in 2 dimensions, the instabilities of the horizontal field tend to look like these mushroom structures. You're looking at the ends of the horizontal field and they have this mushroom-like shapes. And in 3 dimensions, they tend to look, you know, like tubey-like things. So all is good. Things are sort of looking the way you want them to, and that's promising. Oh, and here's a particular calculation I did with Jeff Fassel many years ago when Jeff was a graduate student. This one actually has the layer is created by shear, but it doesn't matter. But here's a nice calculation of tubey-like things being created and being magnetically buoyant. The green stuff is magnetic field, in this case, horizontal magnetic field pointing to the right. Anyway, so not much to be learned from this particular movie, except that you do get structures that you might be interested in. Now, one of the interesting things about that sort of calculation, as opposed to some of the theoretical ideas, is that you don't ever get isolated magnetic flux tubes. You don't get a magnetic flux tube, and you get sort of nice round tubey-like things, but they're not in a zero magnetic field background. There are always magnetic flux concentrations amongst a volume filling field. And the question is, I mean, does this make a difference? And you can immediately think that maybe it does, because if you think of a hose pipe, the flow can only flow down the tube, right? So if it has a surface which encases things, then I can't have any flux out of that encasing surface. Whereas if this is just a concentration, not something which is encased in a flux surface, then I can have flux through that thing. And maybe that helps us out, maybe it hinders, we don't know. But we can imagine that the dynamics may be substantially different. And it turns out that it is. We've done a bunch of I mean, there was some of those experiments, the simulations you saw from Jeff Fassel before. We've done some other simulations before, but we're trying to get at these ideas, and in particular in relation to this whole hemispheric helicity rule from some simple calculations. And this is work done with Bishek Manek, my current graduate student. And all we've done is we want to do a simple 2.5 dimensional flux tube problem, where essentially what we do is we put in a flux tube like I've had before, but we also have a background field. Now, in this case, we've imagined that the background field has some gradient with height, in the sense that it may be sort of more concentrated towards the base of the convection zone. There are these processes, transport processes such as magnetic flux pumping, which may tend to do that. So that's what we did. But essentially, this is just a simulation, whoops, and these are going super fast, whereby all we do is we put in a flux tube, a fat flux tube, towards the bottom of a box with a horizontal field going from left to right, which has varying strength, exponentially varying from the bottom of the box where it's strongest towards the top of the box where it's weakest, which is somewhat representative of deeper solar interior. Now, the cool things we find from these calculations, what you're looking at here is 3 simulations where from the left to the right, the strength of the background field, the horizontal field from left to right, is increased. And as you might imagine, the flux tube has a harder time rising through more field. So on the left, where there's no background field, this is a very standard result. People have known this for years. You know, the flux tube rises up and it whacks the top and it's a mess, but don't worry about that. But it just rises quite easily. And the middle one, it rises a little differently. And on the right one, where the background field strength is 20% of the peak flux tube strength, which is not a lot, but is considerable, then it doesn't rise at all. So you can completely kill the rise of a flux tube by having background field in there. So that's a very interesting result in the first place. And here's some nicer sort of snapshots of that, which you can look at. But these are a little bit more caught instantaneously, so you can see what's going on, where the 0 flux rises nicely. The one that has magnetic field in the background at 10% still rises, but not as quickly as the other one. And then for 20%, it's killed, same result. And there's good reasons for this. Obviously, when you're rising through a background field, you're sort of like stretching elastic bands in the field above you, and so that induces tension. There's also some drainage down that field, so the flux tube can lose some of its buoyant capacity by draining down the background field. And you know, the vortex dynamics of these wakes are drastically altered by the presence of this background field. So there's lots of details of how all that works, but let's not worry too much about that. An even more interesting thing is, if I take this particular flux tube and I just reverse the direction of the background field, so instead of going from left to right, it goes from right to left, then we get different behavior. The rise is quenched from much less strong field in the background when I reverse it. Now, there's one thing I didn't tell you here is that to make this tube rise initially, it has to be twisted. So it has a sense of direction, this tube. So it has a twist to it. So I mean, you may want to just say, well, reversing the background field is exactly the same. It doesn't make any difference. But it does make a difference because there is a sense to the twist and there is a sense to the direction of the background field. And those act together to change the behavior of this tube. So I think I have, here's a comparison of these two things. So on the left is a background where it goes from left to right with plus 10%. So that's a 10%. That's a pretty strong field. On the right here, there's the background field is only 6% of strength, but it just goes the other way. And you can see the bizarre thing is that the one on the left rises, not too bad, and the one on the right is killed. So a weaker magnetic field killed it in this strength when it was oriented in the other direction. Now, like I said, it is actually key that there is twist to this flux tube, so it has an orientation of direction too. So, and that actually is the key to this thing. And just as a quick explanation, think of these are the flux tubes. Imagine it has a twist. So the green arrows show you which way the twist is in these things. And in these two simulations, the twist is in the same direction of both. So it goes to the left of the top and to the right of the bottom in both of these things in this tube. Now, if I insert a background field from left to right, then that's opposing this field in the tube at the top, and it's enhancing it at the bottom. And what that does is change the tension in the tube. So it enhances, so seeing as I've increased the field strength in the bottom of the tube, it enhances the tension at the bottom of the tube. And seeing as tension is related to curvature, it points upwards. So this one actually gets a net upward force. And the other way around, when the background field is negative, then I'm enhancing the field at the top and decreasing the field at the bottom. So there's a net tension in the tube downwards. So obviously when the net tension is upwards, it's a force which aids the buoyancy. And when there's a net tension downwards, it's a force which counteracts buoyancy. So this is the way that we get different behavior between these two things, which is something I think we didn't expect, and probably most people wouldn't have expected. So there's a selection mechanism which says, you can think of this as a preferred direction of the background field or a preferred twist if the background field was kept constant. Like in these experiments, I kept the twist constant and flipped the background field. I could have kept the background field constant and flipped to the twist. It would have the same result, right? Have the same sort of thing. So you can think of this as a selection mechanism which selects, it prefers the rise of certain twists of the tube. So that's kind of interesting because twist is related to helicity, and this is now a selection mechanism which selects certain helicities, right? So, and it turns out, and I don't want to explain this diagram because it will take me too long to explain it right now, but if you consider this in the context of the solar context, then the mechanism we just talked about agrees with the solar hemispheric helicity rules, which was shocking, but surprising, but very interesting. So this is a mechanism which could be considered to contribute to this reason for the solar hemispheric helicity rules. And there are lots more details to this, and we have a nice analytic model which predicts when this works. And the nice thing about this is it only works for a certain number, for a certain range of parameters. There's a parameter regime where this happens, and there are other parameter regimes where it doesn't. For example, if the tube is really, really strong, then it's going to rise no matter what the helicity is compared to the background field. Or if the tubes are really weak, neither of them are going to rise. So there's a regime in sort of strength of the twist or strength of the tube, which dictates that it's in this regime where a selection mechanism operates. So this actually agrees with a lot of the details of the solar hemispheric helicity rule, which is remarkable in the sense that not all tubes obey this rule. And maybe we could say something about, solar cycle dependence from some of these things, because tubes are different strengths at different parts of the solar cycle, etc. So, and we can create synthetic solar hemispheric helicity rules from these simulations by doing Monte Carlo simulations, and they agree with the sort of general nature, or it's actually fairly detailed nature of the solar hemispheric helicity rules, which is amazing. So this is a fun thing. Now, this is not the only theory for the origin of the solar hemispheric helicity rules. There are other theories for do this. Most of these involve convection and rotationally influenced dynamos, which are just some global average of convection, etc. So where essentially the rotation imparts the twist. So it's very interesting to try and figure out which of these mechanisms is the dominant one, whether they all contribute, whether some are dominant in some parts of the solar cycle or some parts of the sun itself. There's a big difference between these other theories and our theories. Our theories is a filter. It says that certain helicities are filtered out and certain helicities are filtered in, whereas the other theories all tend to say, oh, helicity is acquired during transit. So these are different, and it'd be very interesting and entirely possible to try and figure out which is the dominant one of these things. So there's lots to do in this problem. Obviously, what we did was two-dimensional. Really, you need to do three-dimensional problems. And like I said, if you want to start figuring out which is the dominant mechanism, you have to start throwing in things like convection and rotation. So there's lots of work to be done on this, and we're doing it. Anyway, probably my time's up, so that's where I want to stop. I just want to give you some brief ideas of some fun things we've been doing recently in research with graduate students. There's lots of other things going on as well, but this is just one nice little nugget. Anyway, hope you enjoyed that, and I'm going to stop.